For Physics 152, these are the things that you should know cold. So we start out with the concepts. And one of the concepts is parallel. Imagine that you have a river that is flowing, water's flowing along in one particular direction, and it splits. Some of the water goes one way, some of the water goes the other way. And then they join up again. These are parallel structures that the current gets to a certain point and it flows one way or the other, but they do meet up again. This is parallel. As opposed to series, where you have, let's go with the river analogy here. So you have a river that's flowing and it narrows down and then it picks up again into another big area. This is series because any water that's flowing through here is going to flow through here also. So that is series. And even though I was talking about in terms of water current, it same works for electrical current as well. Equipotential surface is a surface where everything is the same potential, equipotential, equal potential. If I have an equipotential surface or an equipotential line, the electric field is perpendicular to that. So imagine that I have a positive and a negative charge here. This is at a higher potential. I would have equipotential lines that look something like this. My electric field, the electric field goes from the high potential to the low potential. If I have a conductor that's in electrostatic equilibrium, my voltage or my change in potential is zero. In other words, if I have a conductor here, I know that the electric field inside is zero and my voltage is constant. And then the other concept is this V stands here for electric potential. This stands for the change in electric potential, otherwise known as voltage. The fact that electric potential is related to voltage, but they are not the same thing. Now, some textbooks will drop the delta. They will treat them almost interchangeably, but officially they are not. Symbols. There are all the symbols right there, so let's sort of take it out piece by piece. So U is the symbol that I use for potential energy. For those who have had me before will know this, and some textbooks use it as well. Some textbooks do not. But U is the symbol for potential energy, just like capital K is kinetic energy. V is the symbol for electric potential or volt, depending upon the situation. If it's a unit, it is a volt. If it is not a unit but a quantity, it's electric potential. That is not the same as electric potential energy. This is just electric potential. The word energy is not there. C stands for capacitance or coulombs, depending upon the context. If it's a unit, it's coulombs. If it's a quantity, it's capacitance. Delta V is electric potential difference, otherwise known as voltage. And I discussed that previously. And then epsilon here stands for the EMF. EMF used to be the electromotive force. It is now the EMF, just EMF. Units, there are all of them. Let's take it step by step. U for the potential energy, E for electric. SI unit for electric potential energy is the joule. That has not changed since the previous course. The SI unit for electric potential is the volt. This gives the really awkward a physics identity where I could say that V is equal to 5V. This says that the electric potential is equal to 5 volts. These V's do not mean the same thing, although they look the same. In math class, V would be equal to 0, but here V does not mean the same thing, and you just have to know from context. This is a quantity here, so this C stands for capacitance, and the SI unit for capacitance is the farad, named after Faraday. This is named after volta. This is named after joule. There are no constants from chapter 19 that are new. Definitions, the EMF. Originally, it was electromotive force. This was thought to be the force that drives charges to move from one spot to another. And then they later realized it's not actually a force. And so even though some textbooks will still say it stands for electromotive force, officially it does not actually stand for that anymore. That is the historical root of it. However, it now just stands for EMF. EMF is in itself just a word. It actually qualifies as a word in Scrabble and Words with Friends. The symbol is epsilon, and this is the ideal voltage. So if I have a 12 volt battery, its EMF is 12 volts. It is ignoring all internal resistance in the battery. It's just sort of the ideal. And then lastly, the formulas. Yay. So we'll take it step by step. For point charges, the electric potential energy, K Q1 Q2 over R, plus some constant. The Q's could be capitalized if it's a collection of charges, or lowercase q for a single charge. Notice it is very similar to force, except for the fact that it's R, not R squared, and the fact that we can always tack on a constant. Electric potential for a point charge is KQ over R plus a constant. I can always add a constant to it. It is similar to the formula for the magnitude of the electric field from a point charge, except it's R instead of R squared. And you can tack on a constant at the end. The relationship between the two, because we actually, when we do the derivation, we derive delta U, and so that's why the constant would just wash out if we subtracted. But this is the relationship between them, very similar to in the previous chapter, the fact that the electric field is equal to Q times F. Very similar derivation. If the electric field is uniform, in other words, constant over a certain distance, then the voltage is equal to negative E dot delta X. If we're thinking through the direction, then we can just do that, and then we will know which is the direction of the positive voltage or the negative voltage. But this is the relationship between voltage, electric field, and displacement. And so combining these two equations right here, we can have the change in potential energy if the electric field is uniform, and all those apply there, is equal to QED. And then we get into the capacitance formulas here. The fact that the general formula for capacitance is the charge on a plate divided by the voltage between the two plates. If it's a parallel plate capacitor, then it's kappa, epsilon sub naught A over D, where kappa is the dielectric constant. And then over here, for capacitors in parallel, the equivalent capacitance is you just add them up. So parallel, I have current that would flow, and then it branches off. It goes across that capacitor, and then they meet up again. Those are in parallel. Whereas series, anything that goes from one goes to the other, that is series, and then the equivalent capacitance is 1 over equivalent capacitance is 1 over C1 plus 1 over C2 plus however many I've got. And that should be the things that you should know cold from chapter 19.